All right, folks, welcome back to CFI 29. So today we're going to start off by reviewing some stuff for the test that's coming up on Thursday. And then the other thing I wanted to do, basically I'll rely on your Muddiest Point Survey responses. But if there are more questions, more things to consider, I'll be happy to answer those as well. So one thing that and then I know there was a lab that I said the first deliverable is due today, but that's all moved by 1 week. So you don't have to worry about that right now. So make sure that you are up to date on your test stuff. And then you can submit the lab, what was delivered, what was supposed to be due today, you can submit it 1 week after. But if you're dead with that, and if you feel pretty prepared for your test, you can absolutely submit that deliverable today. That's perfectly fine. And then you can move on to the next one because the lab itself is quite involved. So it's okay if you are actually done with that. That's wonderful, great. You can actually move on with other stuff. So I did want to talk about sharing my screen and then look at that Muddiest Point Survey here. And I want to project it on the screen as well, but just give me 1 second here. So. Share my screen. All right, very good. So what so first thing I want to talk about, I will start off with the latest material that we covered. So what's going on here? So okay. So the first thing, it looks like you all sort of got the idea of like what is the role of car following models. They determine how each vehicle is going to behave as they lead that. It looks like you all have a good idea about the general car following model, like the GHR model, the stimulus response theory, and what are the key differences between collision avoidance, the more simplistic model, and psychophysical models. They are like GHR model, but based on different thresholds. You just look at different things. Your form of your GHR model changes based on different thresholds, and that's what the last ones are about, the psychophysical models. Basically, what VSIM uses is a psychophysical model because it assigns a different type of GHR model for where you are in that thresholds that we talked about. So this is the key one. These two last ones, I think that makes sense. Those are the more complicated topics here. Significance of different thresholds that define different car following regimes in VSIM. So when I say different thresholds, this is what I mean by that. So let me go back to my notes here so I can talk about those. Let me annotate that. So I'm going to go back down and I'm going to probably switch to student view so it's not as cluttered for you. So I go down to my car following model and I look at I want to look at my car following model. This is the threshold that I showed you in the class. So what is the role of these thresholds? What are the roles of these thresholds in how VSIM does car following? And remember, psychophysical models that are used in VSIM, they're based on these thresholds. And then obviously CLDV, as I said, is not used in VSIM. So there is SDV, there is SDX, there is ABX, and there is AX. You can see that AX, ABX, and SDX those are sort of horizontal line thresholds. Right? What does that mean? That means they only depend on delta x. How far is the distance between the leader and the follower? Okay, so these three thresholds, AX, SDX, and ABX, are sort of horizontal line threshold. And you could see that if you go above these thresholds, so if you go above SDX and you are to the left of this SDV threshold, okay, you are in free driving. You're not in following case anymore. You're not following anybody. So how would your speed and acceleration will be determined? It will be determined based on the speed profile that you have. Remember when we model things in VSIM, we entered like an S-curve looking speed profile. You did that in a tutorial section. And how you had the 85th percentile, like an S-shaped curve, and you specified that the free flow speed would be 45, and then anywhere between 25 to 45. So just basically you pick a speed and you assign that, and you just have sort of a random acceleration deceleration happening for those vehicles if you are in that free driving regime. Okay, so you have to be above SDX and to the left of SDV. So if you're that far away from leader and your speed differential looks to the left of this, then you are in that free driving regime. So that's how. So if I try to sort of draw something out, so if you are in this region, if you are in this region right here, so if you're in this region, here, right, this whole highlight, that means you're in free drive. And then you can see that this SDV and OPDV, so if you look at SDV and OPDV here and OPDV, these are not constant regions. These are not regions that are just straight lines. They are essentially a relationship between delta V and delta X. What is the speed differential between leader and follower, as well as the location differential between leader and follower. So these two thresholds that are highlighted in orange, those two thresholds depend on not just the location difference, but both location difference and the speed difference. Okay, and then obviously, so anywhere when you are between this SDX and OPDV, then you are what we call the following regime, and that's where GHR models are most meaningful. So in this following regime, in this regime right here, the GHR models are most meaningful, right? Because you are in that, your acceleration or deceleration choice as a follower completely depends on what the leader is doing. Okay, and then this, if you go below ABX and you're still moving, your speed is not zero, then you are what we call the emergency regime. That means you are going to try to decelerate as hard as possible to get that, stopping so that you can avoid that collision. Okay, so that's your emergency regime. And then obviously AX is your absolute minimum when you're complete stop. When you're at complete stop, this will be sort of your distance that you will try to maintain. So this is your CC naught that we use in VSIM. Okay, so does that sort of make the idea of, and again, I mentioned in the previous class, these acronyms do stand for something, but what they stand for is in German, so I don't bother with exactly what they stand for. But the idea, because VSIM came out from Germany originally, but the idea is that you have these thresholds that you see. If you exclude CLDV is just like a lower location differential version of SDV. Okay, VSIM just uses one SDV. So I'm thinking, and because they don't disclose the exact model, but if I were to guess, I would think that what VSIM uses, instead of using this 2 CLDV and SDV, it uses a line or an equation or a curve that goes something like this over here. Something like this over here. So instead of these two CLDV and SDV, they use SDV that looks sort of in the middle of these two things. That's how they differentiate between a free driving scenario versus a following scenario. Does that sort of answer your questions about what I'm talking about? So now if you're thinking about how we are gonna, what are we looking at in terms of an exam question, which is a fair thing to ask, because that's how we determine grades and everything. So what I'm thinking is that what I'll do is like maybe I'll give you a figure like this, and then I'll have you sort of fill out. Maybe I can ask you which of these thresholds are purely location based. Right? I could ask you, I could leave out these names and I ask you to pick out which one stands for, which threshold stands for which one. Okay. I could ask you, I could not give you these regimes, and I ask you, what type of regime are we talking about? Is this an emergency regime? Is this a following regime? Is it a free driving regime? Is it a closing regime? So I could give you like 4 blank spaces and have you fill out which portions of this chart are represent car following regime, which portion of this chart represent free driving regime, things like that. So that's kind of what I'm thinking. You should know, depending upon what's happening with delta V and delta X, you should be able to figure out which of these regimes are following regimes, which of these are. So that's what happens in DCM. It's like they look at leader and follower, they look at delta V, delta X, and then they have the whole algorithm of what type of car following model or what type of acceleration, deceleration choices the follower is going to make based on those thresholds. Does that answer your question that we saw in that Muddiest Point Survey? Does that make, like, if you rated that question a little bit lower on your understanding, would you be able to move that understanding a little bit higher on that survey now? Okay. Any questions about this? Good. So that's good. So I can clear this out. And I'm recording this, so in case you want to refer back to it, you could. Okay, so we talked about this. And let's go back now to share. I'm now share the whole screen. So the next question I want to talk about, this is probably what you see also. So this is V2, right? Let me first talk about it. Okay, so the last one. This is basically your homework problem. And I know some of you wanted to submit that homework problem. That's a little bit later. And that's okay. You could do that. Please do that by the end of the lab today so that I can submit I can post the solution. And this is basically what this is, right? So this is mathematically integrate micro level relationships to derive macro level models, like which is Greenshields and Greenberg model. So first thing I would suggest to you is that if you go back to the class canvas page, and if you click on this lecture lab recording playlist, I do have on my YouTube, you come down here. So this lecture, this 36-minute video that I posted, I did mess up while I was recording that in the class, but I did post a new video that kind of takes you over the whole discussion about the integration that we had. So I'll definitely recommend you go over this video. So about a 36-minute video kind of takes you from start to finish. A couple of things I want to still talk about that just to make things a little bit more clearer. First thing is that if you look at this right here. No, I think I want to show you the So one thing that I wanted to note here is that does it not have the? Now let's go ahead and open this PDF. I want to open it in Acrobat here. So if I, oh no, this is, okay. Forget about this. So if I go back to this page 2 here and zoom in a little bit. So first thing I want to mention is that that to be able to derive different macro level speed density relationship that we learned about in CE 321 in our fundamentals of transportation engineering class, is that they're all sort of consistent with the assumptions that we make about car following. Okay, so that's one very important thing to remember, is that if you make certain assumptions about car following, you should be able to derive those macro level relationships. And that's what we did in the class the other day. One thing I would say is that here, in this example discussion that we had, this is from Garber and Hoyle text, by the way. I don't know if I mentioned that in the class the other day, but I should have if I didn't. So this is from the Garber and Hoyle textbook. And if you look at this value of M and L, these values are what lead you to different macro level relationships, the assumptions that you make about the value for M and L parameters. Okay, I did tell you that because if you don't assume M to be equal to 0, the math gets pretty messy. So we are always going to assume M to be 0. So this exponent of speed of the follower, the n plus 1 stands, xn dot n plus 1 stands for the speed of the follower. So we will always put the exponent for the speed of the follower to be 0. Okay, and that basically reduces the numerator to just 1.0, basically just 1. And then this L value we could shift around. So to answer your homework problem, if you assume L to be equal to 2, and then you integrate, because then your exponents become -2, and then when you integrate it, the exponent becomes -1 with a negative sign in the top, in front of it. That would lead you to Green-Shields model when you integrate the things. The important thing to remember here is that you could see a problem like you saw in the homework. I could assign these values, and these variables could look different. Okay, so instead of M or L, you could use O or Q or P, whatever. It doesn't matter what I use. Okay, but the important thing is for you to remember is that M is the exponent for the speed of the follower, and L is the exponent for the spacing between consecutive vehicles. Okay, so these parameters make your following acceleration, deceleration to be more or less sensitive respectively to the speed. That's what M does, and L does, it makes it more sensitive to spacing between the vehicles. So if you increase the value of L, your acceleration, deceleration choices become more sensitive to the spacing. Okay, the closer you are, the more sensitive you would be, things like that. Okay, now regardless of what is being used, and then if you do this, this is the spacing, and then when you integrate things, the other thing you need to remember is that the average spacing, if your flow is in a steady state, your average spacing, if you take the reciprocal of that, that is nothing but the density, average density, right? Because if you have more spacing between the cars, you have lower density. If you have less space between the cars, if the cars have to be too close to each other, then your density is high. So reciprocal of density essentially is your spacing. Okay, so anytime you see 1 over xn minus xn plus 1 that you will see in your homework problem, that you might have already seen in your homework problem, then that becomes your density. Okay, so the key item to sort of note here is that if you do 1 over xn minus xn plus 1, if your steady state condition, that becomes your K, okay, which is density. Now, don't be confused by different nomenclature though. Some books, some problems that you might even see in the exam, they might represent density not with K, but with D. But the idea is to know the concept that it represents, not the notation itself. Okay, so we are talking about the value, the K, either D representing density or K representing density or whatever else representing density. You just need to know that the reciprocal of spacing in a steady state scenario of flow, that gets you the density value. Okay, and again, density is a more macro level measure. Okay, because you're talking about a whole segment and stuff like that. So that's what you're trying to do, is like if you integrate it over time and you have a steady state flow, that's how you have to integrate, because integration gets you from that micro level relationships between individual vehicles to that macro level relationships that you can now apply over a segment of the road. Okay? So that's what's happening there. So this is the key item here to remember. Okay, so this is the spacing, average space headway is 1 over K is density. And then the last thing is that once you are at a point where you have this speed equal to a raised to a times ln 1 over K plus C, this is speed density relationship. And again, you could use a different notation for average space main speed, which is U represented by U in this example, but you could call it something else too. Okay? So once you get to this point, you're pretty much done with the problem, but I would still like you to be applying those boundary conditions. And this is something that you might have done in math. Like, this is what we are doing here is essentially solving what we call a differential equation. Right? We're solving a differential equation. And I don't want to unnecessarily scare you, but if you are thinking about, maybe you've seen it before, if you have ever solved differential equation, that's where you might have seen it. Okay, something like this. So that's where I want to apply the boundary condition. And to apply the boundary condition, I'm trying to think about, okay, at what point is my speed 0? At what point does my speed become 0? So then I can figure out, okay, my speed would become 0 when K is equal to Kj, right? When my density is so high that it's jam density, my speed has to become 0. So at K equal to Kj, U equal to 0. So I can utilize that information. So if I replace K with Kj here, my speed will be equal to 0. And that will help me determine the value of C, the constant of integration. So I can figure out, based on this, I can figure out my C value. I can figure out my C value. And then if U equal to 0, A times ln 1 over Kj plus C. And I can solve for C now. I can solve for C, which is this. And I can plug in that value for C right here in that same equation. And then we know that when you have logarithms, if you have subtractions of logarithms, you can translate that into a ratio. And then that's what's happening here. Okay, so this is a little bit of an algebraic manipulation at the end. That makes sense? Any questions about these? And so this is how you sort of derive. And then if you do because in the case of, so if you do like what we did like for the homework problem, let's say, if you go back here, so it says that right here, the Greenberg's model, if M is allowed to be 0 and L equal to 2, we obtain the Green-Shields model. It says that right here. So if L equal to 2 and M is 0, you get the Green-Shields model. And if you recall, so when you solve for the Green-Shields model, this is what you're going to end up getting. So you're going to get, instead of getting u equal to a times ln 1 over k plus c, you will end up getting this equation. I'll write that down. U equal to minus a times k plus c. And that's what you'll end up getting. If you solve the homework problem, this is what you should end up with. Okay. Now, if you end up with this, this is your Green-Shields model, because that represents that linear relationship between speed and density. Let's see if I can. That represents that linear relationship between speed and density. Density is on the x-axis and u is on the y-axis. Now, what would the boundary condition look like for this scenario, for the Green-Shields model? And we have applied these conditions now in 321, so that's why I did not spend too much time, but I want to make it clear here. If k equal to kj, that means u equal to what? If k is equal to jam density, what happens to your speed? 0, right? It goes to 0, and then that will help you determine the value for c. So 0 equal to negative a kj plus c, and c equal to a kj. Okay, so you can replace that. So that means your equation now becomes u equal to minus a kj, minus ak plus a times kj, right? That's your, and then also in this case though, this is a difference between Green-Shields and Greenberg's model, is that you can actually derive this a value as well, because here the density at which speed is at its max is also defined. You can define this relationship at k equal to 0 as well. Remember, the Greenberg model is logarithmic, so it looks something like this, and these areas are asymptotic in that equation if you look at the Greenberg's model. Okay, so these are asymptotic, so that what I'm about to define for Green-Shields model is not defined, because in Green-Shields model I couldn't say if k equal to 0 what happens. We don't have that definition for Greenberg's model, but we do for the Green-Shields model. So if I plug in k equal to 0, okay, my u becomes what we call the free flow speed, or let's call it uf or u subscript f, the free flow speed. Okay, so I could define u equal to uf, so it becomes uf equal to minus a, this portion goes to 0, uf equal to, if density is 0, a kj. So I can define this term of a kj, okay, to be my free flow speed. So basically what you can say here is that my u equal to uf minus a k. uf minus a. Does that make sense? What's going on here? Right? So we just basically, but again, remember this boundary condition is not defined for the Greenberg's model, because the relationship is not defined at k equal to 0 or u equal to 0, because it's a logarithmic equation. Now, in the test, how might I ask you this question? I will give you different values of m or l, and you should be able to do that integration for me for different values of m or l. The one more thing is that I could ask you, or you could think about, if you know the speed density relationship, if you know about speed density relationship like we did here, what else can you do with it? Can you derive speed flow relationship with it? Can we convert the speed density relationship that looks like this Okay. This is what the speed density relationship look like. Can you tell me how you might be able to derive speed flow relationship? Recall? Right? Yeah.
you have an expression for flow,
Uh-huh.
you set it in terms of that, you have.
Do we know an expression for flow then? So the response I'm getting is that so if we had a relationship that involved flow rate somehow, traffic flow rate, vehicles per hour type of flow rate, we could do it. But do we know any of such expression? We actually do, because if you remember in 321, this is sort of the basic equation of traffic flow, is that Q, which is flow rate, equal to K times U, density times the average speed. Okay, so if we know that Q equal to KU, we can actually change that. So if I want Q equal to K times U, and I want speed flow relationship, so I want this flow, I want the flow, and I want the speed. I want the flow and I want the speed. Okay, so all I need to do is basically derive the value of K from here and plug it over here. So I will be able to get the speed flow relationship. Because Q equal to KU, flow equal to density times speed, is the fundamental macro level relationship that we get for uninterrupted traffic flow on freeways. This is from 321 basically. We talk about where that comes from, but let's just assume that that's true. If that's true, then all you need to do is to do some algebra of finding what the K value will be from here and plug that over here for this K, and I'll have my speed flow relationship. Right? And then if you want to do something else, I could also derive flow density model for this too. Okay, so why don't we do this? Why don't we take maybe 5 minutes to first derive the speed flow, make sure that you all can do it, and then once you've done speed flow, do the flow density relationship for it. Okay, so let's take next 5 minutes to do this, to make sure that once we have the speed density relationship, whatever it looks like after solving this integration problem, we can convert, we can do the easy thing to be able to convert that into either speed flow or flow density relationship. Okay, so let's take maybe 5 minutes to do that. I'll pause the recording here. Okay, so you can. So just remember, all you need to do is eliminate the parameter the variable that you don't need. In speed flow, you don't want density. In flow density, you don't want speed. Just take the value of speed from your model and plug it into Q equal to KU model, which is flow equal to speed times density. Okay, so everybody good with this? Questions? Okay. So first thing we want to talk about difference between static and dynamic. So I'll go to my class notes, and so now all you need to think about is how does the static So this is the key difference that you can see on the slides there. Dynamic traffic assignment extends the idea that we have for static equilibrium, and it does it in two ways. First is it generalizes the static model's perfect information assumption, and the second is equal travel time on all used routes only apply to travelers departing at the same time. So how does it generalize the perfect information assumption? Because now you start looking at what we call the experienced travel time. And now you do it iteratively. So every run of the model, you know what the experienced travel time is going to be based on the previous runs of the simulation, the previous runs of the model, or previous trips made by the travelers. Okay, whatever it is, that perfect information assumption is now based on experienced travel times. So that's one extension. And the second one is that, yes, we still want to have equal travel time for all users. that are using a certain routes. But now this applies only to the folks who depart at the same time. Okay? And that time window, how long you make that time window, determines how far you are from the static assignment. So if you, for example, make that time window to be 1 hour, right? If you make that time window to be 1 hour, that travel time for everybody departing that 1 hour period, and you're simulating the whole thing for 1 hour, then it's basically you're doing a static assignment. But if you make that window smaller, that everybody who leaves between 4 p.m. to 4:05 p.m. Okay, so that makes it dynamic traffic assignment. Then 4:05 to 4:10, and you can make this window smaller, like 1 minute window, or you can make it larger. But obviously, if you make it window smaller and smaller, what happens? That computationally more intensive, right? You need to be able to running a lot of models. And then that iteration that everybody who leaves within that 1 minute period or a 5 minute period has to have the same travel time experience, that will require a lot of iteration between routing choices. But if you make it 15 minutes, maybe it won't be as computationally intense. Okay, so that's the difference. So those are the two key differences between the static and dynamic traffic assignments. And yeah, so that's good. And let's see, what was the other thing? Okay, so instantaneous travel time and experience travel time. Those are pretty straightforward. We talked about that a lot, and I would just simply refer you back to, I should have that somewhere. Yeah, so in this lecture, so this is the lecture where we talked about, I'm not going to play the whole lecture, but I want to make sure. Yeah. So see, instantaneous versus experience travel time, it's a 20-minute lecture. And I think you could go back and we talked about that specific thing. How do we generate the instantaneous versus experience travel time? So you should be able to derive that. That's all in the playlist. And then it's not a very complicated concept either. So I'll let you figure that one out. Let's go back to my survey here. Okay, so experience travel time. So yeah, so same thing. So instantaneous and experience. Please go ahead and watch this video that I just talked to you about. So this is from April 14th. If you want to note it down, if you're not clear about instantaneous versus experience, there will be a problem based on that. So make sure that you understand that clearly. So the lecture video from April 14th should have that. And then let's see what else was there. Okay, so yeah, so this is an important problem, and I want to talk about that a little bit, maybe in the context of the homework problem that we had. So let me go ahead and share the homework problem on. And I know some of you were able to solve that homework problem, but maybe we can introduce a little twist to that, and based on that, figure it out. And it's a complicated problem when you have existing traffic. I think this was the homework 3, right? Okay, so this is the problem we're trying to solve here. This was the problem, but let's do one thing, just to kind of give you some more experience with this. Let's change some numbers and try to resolve this problem in preparation for the test to make sure that we can solve this. So what I want to do now is I want to solve this problem, but I'm going to try to annotate this here. Okay, so instead of this being 5,000, okay, so instead of this being 5,000, I want to change this number to 4,600. Because the problem would be very similar to this, right? So 4,600 vehicles per hour. The link performance functions are the same, But now I'm going to play around with these three numbers too. They're part of a larger network, and then these are the flow values: 800, 900, and 600. So these are the existing flows on route 1, 2, and 3. Okay. So route 1 has existing 800, route 2 has 900, and route 3 has 600 vehicles per hour. Okay, so with that, I'm going to have you work on this for a little bit and then come back and talk about this right now. Okay, so let's spend some time, maybe next 5 minutes or so, thinking about this problem. And again, you don't have to solve this part. Okay, you don't have to solve the part where, so I'm going to cross this out. Don't worry about this one without any pre-existing flow. Okay, so I'm looking at dividing this 4600 flow with these numbers. Okay, so then obviously this number is not 4500, this number is 4600. Let's make sure that we can solve this problem. Always think about the pre-existing flows also. So the question I'm asked is like, for this type of a problem, if you try to solve it, it's a 3-equation, kind of a matrix, could be very challenging to solve in the exam setting, especially given the exam is only going to be 50 minutes. So yes, I will be mindful of that. And what I will do is, I will have you all just give me the set of equations. Give me the set of equations to be able to solve. So I'll not ask you for the final answer. I'll just say, give me a setup of equations. If I feel that actually only 2 routes will be used, so then, I might ask you to actually solve the problem. Okay, so it just depends on what the problem looks like. And it's possible that I can give you just like, okay, give me just the setup of the equation rather than giving me the full problem. Anyone has not solved, but are there questions about this? Anything? Any questions about this problem so far? Okay, so we'll try to solve this problem. So x1, x2, and x3, they have some pre-existing values. And again, all of these are thousands of vehicles per hour. So I'll do 0.8, 0.9, and 0.6 for the 3 routes. And T1, T2, T3, this time I might have a different order for your sheet. So be careful, because I think we were doing T1 and T2 in the problem here, and then T3 was here. But that's okay. It shouldn't matter as long as you're careful about how you're numbering it. Okay. So what I'll do is, like, I'll first figure out the initial values of travel time given those pre-existing flows. So instead of free flow travel time decision making, now I have to decide based on the pre-existing flow that exists on these routes because they're part of a bigger network. So I got initial values of travel time. T1 naught, it will be 6.4 units. 2.2. And this one, does this make sense? So I got 6.4 units of the travel time at the beginning for route 1, 7.6 for route 2, and 16 units for route 3. Did I do it right, or did I miss something? Is that not 16?
Yeah.
Okay, because because it's 17 times 0.6 is point. Yeah, because the 2 decimals here. So what's the total number here? 6.82. Is that what everybody got? Okay, good. So yeah, because I was multiplying by 6 rather than 0.6. Okay, good. 6.82. So your route 2 is at the highest level of travel time, but it's not that much higher. So I can sort of, in my head, I can tell that it looks like all three routes will be used. Again, obviously you want to verify it, but I can tell because this travel time is not that much higher from 6.82 and 6.4. So in my head, I sort of had an idea that the threshold for all three routes to be used by this flow of 4,600 or 4.6 in thousands of vehicles per hour is actually going to be, the threshold for all three routes is going to be pretty low, and the 4.6 will easily exceed that. It's just way of thinking about it. But your decision now will be based on 7.6. So you want to figure out at what point the travel time becomes 7.6 on route 1, and what point does it become the 7.6 on route 3. Okay, so you try to derive those numbers next to be able to see how many routes will actually get used. So I'll do 4 plus 3x1. Okay, and this x1, when I put it like that, x1, x2, and x3 represent the total flow. They always represent the total flow if you write them as these variables. You want that to be equal to 7.6 to figure out what will be the value of x1. And similarly, so you can solve for x1 here. So 3.6, 1.2. So at one point, when x1 becomes 1.2, i.e. new flow of 1.2 minus 0.8 equal to 0.4. Okay? And then you can solve for x2 as well similarly, or not x1, but x3. So when 5.8 plus 1.7 x3 equals to 7.6, and then what does that become? 1.8. Okay, what does that become? 1.8 over 1.7. What does that mean? Does anybody have the number here?
1.06.
1.06. Okay. Okay, so that's the total flow, and then i.e. the new flow of 1.06 minus 0.6, right? Because existing was, so that becomes 0.46. Okay, so x1 can take in new flow of 0.4 units, and x3 can take in new flow of 0.46 units until its travel time becomes competitive with the route that is at the risk of not being used. Okay, so what your threshold is now? What is your threshold for total flow between OD pairs that will get you to all three routes to be used? You just add these two numbers up, right? So the total flow at which all three routes become used is total OD flow at which all routes become used, all routes are used, is 0.4 plus 0.46, 0.86, which is 860 vehicles per hour, and it's less than 4,600. Use all three routes. Okay. Now there are a couple of ways of going about doing this. The way I like to do it, the way I prefer to do it, is I will start equating all three travel times for the OD pairs, right? For these OD pairs, the travel time would have to be equal. Okay, for this OD pair, travel time ultimately, when the equilibrium comes, the travel time on all three routes has to be equal. Okay, so what I'll do is I will say, instead of pre-existing now, I will try to do my travel time to be equal. So I'll set it up as, so I get 3 equations and 3 unknowns. So I'll set it up as 4 plus 3x1 equal to Okay, so that's how I'll set it up. This one. Okay, and then I'll say okay, so this has to be there. Okay, so I'll get those two equations going. And then I can just simply do x1 plus x2 plus x3 equal to 4.6. That right? Not right, right? Yeah, go ahead.
You need to add the pre-existing.
Yeah, so see, I'm representing x1, x2, x3 as the total flows that are using those routes. So I cannot simply say that x1 plus x2 plus x3 are only 4.6. They're not. They're actually 4.6 plus whatever existed when we started solving that problem, which is 0.8 plus 0.9 plus 0.6. So x1 plus x2 plus x3 should be equal to the new OD route flow plus 0.8 plus 0.9 plus 0.6. And now that whatever equation this becomes, so 4.6, 6.9. Okay. So now I have these equations, x1 plus x2 plus x3 is 6.9, and then the travel time being equal. And remember one thing about this though. And again, this may become moot or this may not become moot in your problem. If I ask you to just set up the equation, then you're done pretty much. Right? But remember, these x1, x2, x3 still represent total flow rates that are using that route. Okay, but if I'm asking you to divide what happens to that individual flow rates, 4.6, then you have to subtract that from the individual answers. So if I ask you, because that's what I'm interested in, what portion of that 4.6, what part of that 4.6 goes to route 1, route 2, route 3, remember, the answer that you're going to get from these equations, does anybody have solved it from using that? Yeah.
So are you asking about the answers for like
The total answers, not the individual answers. If you were to solve x1, x2, x3 from these equations, what do you get?
I saw it.
Will you solve it differently? Okay. Can anybody quickly give me the answer using this equation, and this one, these three boxed equations? Yes.
I got x1 is 2.3, x2 is 1.5, x3 is 2.1. x3 is
3 point, yeah, that's right. So Lauren tells me that these will be your answers for x1, x2, and x3, right? The problem you can see, I hope, if you add them up, they add up to 6.9, which they should. They should not ask for 4.6. Yes.
So I'm curious if we want to solve it like different ways.
You are welcome to solve it differently, and we can talk about that in just 1 second. Yeah, so there is another way of solving that, and that's perfectly fine as well, as long as you keep track of what's going on. Okay, as long as, because I think that other method would require, and we can come back to it, would require you to think about x1, x2, and x3 somewhat differently. Like, you probably consider x1 prime, x2 prime, x3 prime, some new variables, which we can come back to in a second. But if you just solve these equations, you'll get these values of x1, x2, and x3, which is great. It's the right answer, but it may not be the answer that I'm looking for. I might ask you, give me what flow out of 4600 goes to route 1, route 2, route 3, and that's not this answer. These answers are not that. To get those answers, you have to subtract from this, and you can call them x1 prime, x2 prime, and x3 prime. Okay, so these prime values will represent what portion of 4600 goes to which network or which route. So you will subtract essentially x1 prime will be 2.3 minus the existing, which is 0.8. x2 prime will be 1.5 minus 0.9, and x3 prime will be 3.1 minus 0.6. Okay, and then you could get that way, you could get the answer. So now you can talk about what was the other way that you were mentioning. What would you do differently here? What would you do?
I would just like you can solve it by changing the throughput time on here, the throughput time on each one. So take a C minute. And then when you solve for x1, x2, x3, you just get the values without.
Yeah, so that's one way of doing that. So the other way of solving that might have been that instead of sort of, you know, how we derive the pre-existing travel time. Pre-existing travel time was 7.6 on route 3, and then whatever it was on route 1 and route 2. So now you make those the free flow travel times, and then you change this equation to x1 prime, x2 prime, and x3 prime. I think that should still give you the right answer, because that would, you know, it's fine. Like it will give you the right answer. I sometimes wonder, and I'm not going to give you that type of problem in the test, so you could probably go ahead and solve it this way. I sometimes wonder though, a situation could arise where, because you're, I guess, if you're not careful, you could end up with the wrong situation. I can't quite think of it this way, but just as long as you remember that now your equation represents different values. So you want to change that equation to say x1 prime, x2 prime, and x3 prime. So just new variables. If you were to take that approach, I would just always write them as x1 prime, x2 prime, and x3 prime. Okay, just so that I remember that I've changed my link performance function. My link performance function has been changed. Okay. All right, that's good. So then that's what I wanted to cover in this one. Let's see if there was another thing going on here. Experience, this one we talked about that. Yeah, so we talked about everything. And I did go over the other two Muddiest Point surveys already. So that's fine. So now let's talk a few minutes about what the test is going to be like. So let me clear out this. So clear it out. Okay, so I did send you all an email. So I don't think I need to worry about this. Okay, so the last thing I wanted to talk about is how you're gonna, about what the test is going to be like. So test will have some very simple fill in the blanks or multiple choice type questions. They will relate with like conceptual things that we learned about, you know, what is simulation, or the lab that we did on estimating the value of pi, is that static or dynamic, things like that. Okay, so that's obviously static simulation, because that doesn't account for there are no changes in the system that happen because of time spent. So things like that. So that's one thing that we'll talk about in the test. There might be questions like that. And then I might give you a very simple network like this and ask you, and this is sort of related with some of the things that we were doing in the lab. I'm not going to ask you to say, hey, how do you model right turn on red or anything like that? That won't be part of the lab or the part of the test. But I could ask you, in a simple network that we solved, I could give you a breakdown between, I could give you what is the input flow that I'm providing here, maybe 500 meters per hour. Okay. And I can ask you, hey, if I want maybe 60 vehicles to show, maybe not 60, but let's say 100 vehicles to show up here. Okay, what should be my OD breakdown? That I want 100 of these vehicles to show up here. What should be my OD breakdown for that problem? So how much flow would you put from here to here to get 100 vehicles from here? 20%, right? So you will put 0.2 in your OD matrix. So I might ask you to do some kind of fill in the blanks like that, just to kind of think about. And why is that type of thinking important? Because as you're doing in your homework, in your lab assignment, you might want to think about, okay, am I getting lower flow or higher flow here? So which of these factors should I increase? when I'm doing validation and stuff like that. So that's why I'm just going to give you some very simple problems like that to figure out. And then you could say, okay, if I have 500 meters per hour here, if I have 100 from here, and I have 300 from here, and then so it will have 4 different origins, right, that could contribute traffic to it. So these are all input volumes that I'm specifying. Okay. And then I could give you 300, 500, 100, 600, and then last input value is 400, right? Let's say. And I give you all the percentages of traffic that leads you to this point, this destination points, okay? And there could be multiple destinations, but let's say if I gave you that destination, and I could give you the relative flow that go from each origin to this place, I could ask you, what is the expected vehicle count at this destination point that you'll observe? Yeah. So I could give you, like, the 5 different sort of OD pair. So maybe, so let's call it zone 1, 2, 3, 4, 5, and 6. Okay. And then for destination 6, this is what the percentage looks like: 0.1, 0.2, 0.4, 0.6, and 0.2, something like this. If these were the OD pairs to zone 6 from zone 1, 2, 3, 4, and 5, can you get me what is the expected amount of traffic that you'll expect on this destination? Right? You should be able to give me that. How is that? Because 400 is input, and out of that 400, 10% is going to this destination. So this will contribute 400 times 0.1. This will contribute 300 times 0.2, because 300 is input from here and 20% goes here. And then same thing plus 500 times 0.4 plus 100 times 0.6 plus 600 times 0.2. And then you can add them up, and then that will tell you what percentage of traffic can you expect at that destination point. Okay? So some simple problems like that. So some true false, multiple choice, fill in the blanks type questions. Maybe I'm thinking maybe 4 or 5 like that. And maybe I'm thinking one problem on instantaneous and experience travel time, one problem of that user equilibrium, and one problem on this the integration. So this might seem like a lot, but I'll make sure that you can cover it up in 15 minutes. So it won't be too much. And obviously, if you do poorly, not terrible, because you can make it up in the finals. So I don't want you to do poorly because I don't want great finals myself. So my hope and expectation and prayer is that you just all excel, and I just have to grade these 2 tests, and nobody shows up for the final. But it's okay. If you do badly, you have another chance coming. So, but I think you'll be fine. You don't have to worry too much about it. And then the final obviously would be like these tests. There will be different problems, but just like this. So, and then the final, the test is going to be sort of open everything except for any electronic devices. So everything else you could use. I know I was asked about, like, if we could use iPad. I can't let you use that because then I can't police, like, if you're communicating with other people. So, but other than that, it's going to be open notes, open everything. Yes.
With electronic devices, does that include, like, can they use a computer to look up the campus?
Yeah, that's what I'm worried about. I don't know. Yeah, because then it gets very hard for me to figure out what you're looking at. So I would suggest that your best bet might be just to review the material and maybe come up with like 2-3 pages of stuff, and then just there will be nothing that's completely based on memory. I don't think there will be anything that will require you to kind of remember anything. It's just going to be conceptual questions, and hopefully you can sort of derive that from your in the past I've done it with where I've just asked folks to just bring in like, one page full up, front and back, you can write whatever you want on it. Is that something you would prefer? Instead of completely open notes, just one page of front and back? No, right? So you would want to have more flexibility. Yeah, so that's fine. Yeah, so that's what I heard too in previous years, that just bring whatever. You don't, I mean, I don't know. I'm really sort of conflicted about this. I don't know what's the right approach to take as a student. I mean, yeah, so as long as you don't have any electronic devices, if you want to print the whole notes out, be my guest. If you want to print those slides out and print them as PowerPoint and then 3 slides on one side and notes on the other side, that's perfectly fine. I'm good with that if you want to do that. And then you can bring in whatever, you just cannot use other people's help, but other than that, everything's okay. All right, with that, I'm going to stop the discussion about the test unless there is something else you want to ask about. Anything else about the test? Okay, so we'll start that on Thursday in the class. And then if you want to, it's up to you if you want to prepare for the test. Make sure that you look up the video, all the YouTube things. I tried to be like, you could see what we are covering that day, or like, and then you could see, what's going on in that. And like, if that it's not there, then it's in the description usually. So try to put, descriptions in there. So yeah, you might be able to, so look through these videos. There are a lot of them, but depending upon what you're trying to do as you're reviewing the notes, if you get some questions, you can go back to every lecture has a date in there too. So you can sort of guess what's going on. And if there is anything that will make it easier for you to look up these things as you're preparing, let me know. I'll try to maybe add some things there, but that's all I have got going on. Okay. All right. So I'm going to go ahead and stop the recording and stop sharing. All right, so first.